Our next speaker is Sage, who is going to tell us that all of us should build a robot. I'm not sure if I should use the singular or plural pronoun for that, but there's a y'all in there somewhere. Sage is an AI engineer based in Seattle, but honestly, when I asked about Sage, if there was anything that I should say on the intro, earlier, everybody else in the green room told me to say that he is a really good clapper. And if you've heard very loud clapping from the back of the room, that is apparently, this is the man responsible. So on that note, give him a big hand.
Developers. I'm going to do this talk. This is the last, I think, of this talk format before break and then panel. And it's titled, You Should Build a Robot. And it's really a quick introduction to MicroPython and microcontrollers. Why you should build a robot? Well, one, I think for fun is the best reason. It can be really educational too, and especially maybe if you know someone or you have a kid or someone who wants to learn programming, having something like physically move around and react with what you program, I think is really fun, and I think people tend to agree. There's also a lot of practical applications that you could build and like solve problems in your house or at your company by learning how to interface with hardware and make it do stuff for you. And I've done both of those, like both professionally and then just like kind of weird, sometimes kind of dumb use cases around my house to save time. And that's why you should build a robot. That's my talk. Just kidding. For this talk, we're gonna go build this kind of small, maybe not the most beautiful looking robot, but there's a reason for that. Like this is I had this idea of building a kit that people could assemble for around under $20 or around $20 and learn all the basics and being able to use all the basics of a microcontroller with MicroPython. So we're gonna go through and kind of build this together a little bit, and I'll do an introduction to microcontrollers and MicroPython as we go. Before we build, who has thought about building a robot or maybe something similar? Quite a few people. Who has done something like that? Less people, but a fair amount of people still. Awesome. What's like a microcontroller, something you've used? ESP32, awesome, great. That's a great microcontroller. We'll talk about a few options for you to choose from. Does anyone else have a pile of stuff like this in their house? I think more people raised their hands and said yes, they've actually built something. So I know I bought stuff and then it sits around forever. Hopefully this talk can maybe kind of break down the barrier for you to get started with that. And I assume who here knows Python, at least enough to do stuff? So if you know Python, you can interface with this hardware, and we're gonna see how with MicroPython. A quick personal example. Has anyone happened to play the game Vermintide 2? No one. Well, I sunk like 600 hours into it, and you win chests with like better equipment and stuff in there. And then at some point, I had hundreds or 1,000 chests, and you had to press the spacebar every single time, and it would take me a long time. And so I thought, well, I could just do this with like a servo and a Raspberry Pi and MicroPython. And this is a really kind of a dumb, funny example, but it did save me a lot of time. And then I've actually done things very similar in a professional setting where working as a hardware engineer or reliability engineer, I had to like press something thousands of times or millions of times before it failed. And I would press it and then measure something with another sensor to see what was happening and then kind of log that over time. So like this is kind of a funny thing, but also there's a lot of really good applications actually just where you might need to click something a ton of different times. So what is a microcontroller, or often called an MCU? And it doesn't stand for Marvel Cinematic Universe. I feel like they kind of ruined this acronym now. But it's a self-contained computer on a single integrated circuit, and it usually includes, or it always includes, the processor, which executes the instructions that we give it, has memory, both RAM for temporary storage and also flash or EEPROM, where you're gonna store like the program that it's gonna run. And then it has pins. We'll talk more about these pins in a little bit, but this provides input and output and ways for us to interface with sensors and moving things like the servo we saw, reading in data like temperature, whatever you're connecting it to. And then it has built-in things to make that even easier. So there's something called an ADC. We'll use this a little bit later. But that's called an analog to digital converter. So you can have an analog sensor, like a temperature sensor, and then that gets converted to digital, and then you can program your chip to do something around that data. They're also really low powered, and they don't really have the overhead of running a whole OS. You're kind of running this on the bare metal. And so someone mentioned ESP32. There's a whole bunch of different options that you can choose from. The one that we're using today is going to be the Raspberry Pi Pico. They're around like $4, I think, or they were. They have a newer version, so the older one might be even cheaper now. There's a whole bunch to choose from. And choosing one, you would just kind of see, can it do the things that you want for your project? Does it have enough pins? So you can see like some of these have half the amount of pins, some have way more. So like, do you need to connect a lot of sensors to it? Do you just need one? Do you need different outputs? This ESP32 kit has a little camera on it, so you can actually do embedded vision as well with things like MicroPython on these really tiny chips. And once you choose one, they're always going to have like a layout like this. I'm not going to talk about every single thing in here, but again, you might use this to make a decision on the chip. And then once you have that decision, it kind of tells you where all the pins are. So we can see here, this says like GP27, that just means the general programming that can do input and output. And you also see some things that say like ADC1, that's the analog to digital converter again. So you can look at the chip, be like, how many analog sensors do I need? Does this chip have all the things that I need for that? And then kind of the basics. Again, there's more to microcontrollers, but really most of the basics to be able to do the stuff that you want. It's going to be digital in, where you're reading a binary signal on or off, kind of coming into the chip. And that could be something like a button. You push it, it's pushed, or it's not pushed, right? Then you have digital out. That sends a signal out of the chip that could be turning something on. So a common hello world of like these applications is turning on an LED at just one level of light. So you turn it on, turn it off. And then you have analog in, like we talked about. That reads a continuous value. So again, I think temperature is a good kind of thing to mention. Like, that scales, right? It could be 30 degrees, it could be 80 degrees, and you want to be able to read that in and do something based on that data. And then there's something a little bit more complicated called pulse width modulation. And for this talk, you can kind of think of this as it sends out a more complex signal from your chip so you can control more complex parts. It can also simulate analog out. So if you want to have LEDs at like fade in or fade out, you can use this thing called pulse width modulation. And we'll see kind of all these things in action here in a little bit. And what is MicroPython? So we tell the microcontrollers to do all those things we talked about with code. A lot of times, if you've done embedded stuff before or you've looked at it, you might have seen that you had to use C or C++, or that was recommended. Now a lot of chips have enough memory, and now there's a library called MicroPython, which is a lightweight version of Python with Python 3 syntax, and it has a limited subset of the standard libraries like time and stuff that exist in Python. It also comes with other libraries that help you to control the hardware components. So like all those pins we saw with the digital in, digital out, analog, etc. That's kind of built into a library where you can easily interact with it with MicroPython. And it's designed to run on all those microcontrollers we talked about. So actually the person who did the ESP32 before, did you use MicroPython? CircuitPython, which is, I think CircuitPython is like a fork of MicroPython, or I could be wrong. It's another version very similar, maintained by Adafruit, I think, which also, I'll mention them later, but Adafruit is a really good site if you want to buy these like microcontrollers. And it's compact enough to fit and run on almost any chip within just the 256K of storage space and then 16K of RAM, which most microcontrollers have that now. So it's kind of cool. Like it used to be harder to run MicroPython and stuff, and now almost everything you can kind of easily get it on there. And then setting it up on the microcontroller varies on the microcontroller you choose, but for a Raspberry Pi Pico, it's very easy. There's a button on there. You just hold down that button as you plug it into your computer, and it kind of becomes a USB stick. So it's mounted, and then you can drag and drop stuff onto it. And you're just going to drag and drop a specific file that you download from Raspberry Pi Foundation. They have ones for the specific boards. So even the Raspberry Pi Pico, now there's at least Raspberry Pi Pico 2. And then they also have a version that has Wi-Fi. So when you're selecting chip as well, you can see, does it have Bluetooth? Does it have Wi-Fi? Do I want to do like IoT stuff and communicate data to other devices in the house? Once you drag that on, then you are ready to basically program it with MicroPython. And actually, if you wanted to, you can also just drag on .py files at this point. So once it's loaded in there and mounted, you could also drag in like a main.py, and then it would run on boot up once you kind of boot this after you unplug it from your computer. But a better way to do that, I think, at least for beginning and debugging and stuff like that, is actually using an IDE for it. And if you're just getting started and you don't want a ton of headaches, I recommend using this one called Thani. It comes with MicroPython, so when you install it, it has MicroPython already downloaded as well. And it connects so easily to the Raspberry Pi Pico, like when you plug it in, it knows what ports to look for. So I've actually never had a problem with it like not finding it when it's plugged in. I'm sure it will happen sometimes, and you can debug it that way. But it's scarily easy sometimes, where I thought it was going to take me half an hour to an hour to set this up for, like on a new machine a few months ago, and I just downloaded it and it worked, which is really cool. And it's available on Windows, Linux, and Mac OS, so it makes it really easy. Like I mentioned, easily connects, so when you program in here, you can hit the save icon or run icon, and at least the first time you do it, it's going to ask, like for the session, every time you click this, do you want this to run on the Raspberry Pi Pico when it's plugged in and it found it? Or do you want to save it locally, et cetera? And then you also have a terminal down here, which is the REPL for your microcontroller as well. So you can like print out values and debug it, and it'll actually show up here. So for example, if you have a light sensor, like we'll see with MicroPython here in a minute, you could print those values here and kind of debug what's happening, which is also really useful. Again, that needs to be plugged into your computer for that to happen, but it's a great debugging tool. And then also comes with a MicroPython interpreter, so it kind of knows what to highlight and what errors might be going on. And then hardware setup for this at a high level is we're going to use one Raspberry Pi Pico microcontroller, one solderless breadboard, and a solderless breadboard is just a way for us to plug in components without having to solder anything. And it makes it really easy for you to kind of build this robot kit without having to use a lot of tools that you might not already have. One small battery pack. I actually just use like a really cheap phone charger that probably won't even charge my phone fully once, but it works great for this. And then two continuous servos, and servos are kind of a special motor where you can give it a signal and it'll go exactly to that place, like 180 degrees, et cetera. Continuous servos are a little bit different, where instead of going to an exact space, you can give it speed controls, and you can also go forward and backwards just by providing a signal to it. And then a couple resistors. Resistors are just a way to kind of tone down the voltage or current going to those components. So if you just connected the LED to the board, it might blow out because it was too much voltage, and you just have a resistor in line. We have two LEDs that we're going to light up, two cadmium sulfide photocells. Those are just photoresistors where the more light that's on them, the higher or lower the resistance will be. So we're going to use that for our light sensors today. And then you can use switches, which I have in the photo, or I'm going to show you real quick. I really kind of like making my own switches for things like this with guitar strings, and it gives it a little bit more character. And also you can kind of fine tune it to do different things. And again, this was kind of designed to be like around $20, and that most people could build this. So putting the hardware together, again, almost no tools. And that's why it looks the way it does. I purposely made this kind of really messy, where it's like you can just use tape, you can use a rubber band, you can make this way better. So like I didn't even trim any of the wires. They're all sticking off kind of weird because I just wanted to show you could plug them into the solderless breadboard. But you could tape the servos, you could hot glue the wheel. So usually servos will come with a little attachment like this. This isn't like a tire or a wheel. I just put a little bit of hot glue so it has some traction and it can actually move around. But again, you could make this look a lot neater if you wanted to. But just kind of want to illustrate, you don't need fancy tools or a soldering iron to get started. To make our little antenna switches, which again, we could use normal switches, but I like making my own. It kind of makes it feel like a bug too, and I don't know, I like that in my weird little robots, I guess. A switch is really just two pieces of metal, and when they connect, they're connected and it passes voltage in, and then that's how we're gonna know that our robot in this case kind of ran into something. You could also kind of customize like where these antennas go. You could add a weight onto the bottom, so when it drops off an edge, it also triggers it, and so you could actually use this for like ledge detection. And then the circuit, I'm not really gonna go too deep into this, but this just kind of shows how it's all tied together. Really the important thing for going through the code next is the pins. So we can see that we have two servos, they're connected to pin 1 and 2, and we have two LEDs, 15, 16, two of those photoresistors, 26, 27, two touch sensors, or those antennas, or the switches, and those are pin 14 and 13. And then, all right, so let's go ahead and program our robot together here. We're going to make it drive forward, backwards, turn. We're going to see light levels, so you could program different behaviors, but we're going to make it go towards light in this case. And then we can detect object collision on both sides with those little switches. And then we'll also light up the LEDs to kind of communicate when something happens. So first, we'll kind of do a hello world by making our LEDs blink. We're turning something on. So out of all the stuff I talked about in microcontroller, what do you think this would be? Digital in, out, analog in, or PWM? Someone has to say it. Digital out, exactly. So we want to turn something on, so we're not looking at any data coming in, and we're not, in this case, we could use PWM to kind of fade these on, but we're just going to turn them on at a consistent power. So we import the library machine, which is, again, a MicroPython thing, and that's going to allow us to import pin, which we can define the pins that we kind of want to mount to and tell the microcontroller what's going on with a pin. We're also importing microtime, which is a time library in MicroPython. So we're just assigning our left and right LEDs to those pins that we mentioned before. That's where they're at. We're saying they're going to be a pin out, so digital out. And then we just have this little while loop. We're setting the value to 1. That means on in this case, waiting half a second, and then turning them off. And now we're able to make our robot blink at us. Now we're going to add the touch switches. We want to make our robot feel. We're providing feedback to the robot. It's just something turning on or like connecting. Which one is that? Digital in, right. So again, it's not analog. It's just saying something happened, like it's connected or it's not. So very similar to before, we imported the same libraries. We have the same LEDs at those pins. Those aren't going to change. You'll see them throughout, I think, all the other examples here. And then we assign our inputs to these pins, 14 and 13, and then we just have a while loop again, and we're saying if the right is equal to 1, which means when it's connected, it's going to turn on the LED. Otherwise, it's going to be 0, and then same with the left one. And then we're going to make our robot see light levels. Which one is this? I think you know the drill now. Analog, I feel like, and way more people are talking now, it's great. Analog in, right, you're right. So we are going to be looking at light levels. Again, this resistor value changes based on how much light is coming in. And we're importing the same things, same LED pins. Now we're assigning the photoresistor right and left to ADC. Again, that's analog digital converter to those pins. And then we're reading it in as a unsigned 16-bit integer, so it can read in values from 0 to 65 plus 1,000. And if we were to print this out in Thonny, like you'd see these levels go up and down all the time, like if you're shining a light on it. And then in this case, just in our while loop, we're basically just saying if the right is brighter, then turn on the right LED. And if it's not, turn on the other one. Now, one last thing, we're going to make our servos drive. This one is a little bit more complicated because if it was just a digital motor or a regular motor, it would be like a digital out potentially. But what do you think a servo uses? PWM, everyone's got it right. And hopefully you can read this code. It's getting a little small here. But again, importing all the same stuff. PWM works a certain way where you set a frequency, and most servos have a frequency of 50 is how they read the signal that's going to come out. And then you have duty cycles that you pass in. Again, you don't have to memorize all this right now, but basically for these servos, this is the data that we pass out when we want them to stand still. And then there's a certain value we pass out when we want them to go forward. And there's another data that we pass out when we want them to go backwards. And then I kind of messed up my naming convention a little bit here because I just said servo forward. But one of the servos is flipped when I put it in the robot. So I really should just rename this like direction 1 and direction 2. And now I have these functions here where, like you can see, this is the stop. So none of them are going to be moving. Then we have move forward, and one of them says backwards. Again, confusing because I named it forward. Again, it should just be direction 1, direction 2. I think that would be better. And then we do the same thing for move backwards. And then we just have this little while loop. So it's going to move forward, sleep for half a second, stop, move backwards, and then kind of just repeat this forever. And then putting it all together, can everyone read that? And I made a terrible joke saying, now that is MicroPython, because it is really small. But we put it all together, and actually before I go out of the slideshow, you can see that it's now going towards light, and then I threw kind of a ball in front of it. It has a collision sensor, so it kind of backs up, turns around. And in this case, the sun was actually coming through this window, and it got pulled over towards that light then and started going that way. So we kind of combine all the things we just talked about to create that behavior. And I won't go through like every single line here. This is just kind of all the stuff that we already did, but put together. So we assign all our sensors and actuators, our outputs here, and then we just define how it drives. And then we have a little light follow function that just reads in the photosensors like we already did, and that says if one is greater than the other, turn towards it. And then we have just the while loop that also looks for the sensor detection, or the collision detection. And I'm running a little low on time, so again, this code is also on my GitHub. You can go to Sage Codes. It's one of the pinned repos. And I'll actually do like a full, I think, blog post, a little bit more in depth of like putting this together. And I can, I'll put the slides on GitHub too. I don't think they're on there right now. Some suggestions when you're getting started. Again, Thonny is fantastic for getting started if you don't want a headache of setting anything up. Change the robot behavior. Definitely make it your own. You can do things with all the same sensors we had to, like you could actually point those photoresistors down and have it follow a line. You could try different sensors. So we are only using a couple that exist. You have different ones that can detect objects further away. You have like moisture sensors. If you wanted to have something automatically water your plants, there's a lot of really cool little opportunities for you to use different sensors to do stuff. And then one thing too is you might want to consider using an inexpensive computer to program it first. So if you do short a circuit and it's plugged in, like potentially it could fry your USB port, and that might really suck if you're using like a $3,000 MacBook or something like that. So you can actually take like a Raspberry Pi, set up Thonny on there, and then program on there. And I do that sometimes if I think I'm doing like a risky thing and it might short out. And then also, it's cool, you can write this in Python, but maybe you want to go further into the embedded space, and you could try converting it to C or C++, or maybe even Rust. Try a full Raspberry Pi. You don't need MicroPython for that, but it does have the inputs and outputs, and you can actually build a more complex robot, maybe using like cameras and doing computer vision. Again, you can find all these parts that we talked about on Adafruit, various other places as well. And obviously, most important is to have fun. But one last thing. So I know also quite a few people here are from Seattle. I'm in Seattle as well. And I'm thinking about doing this as a hands-on workshop. So I'll buy parts, and then people can come in and actually build a robot, and then maybe we have like a challenge or something. Who would be interested in doing something like that? Some people. Okay, a lot of people. Perfect, awesome. We'll keep an eye out because at least we'll probably do that in Seattle. Maybe there's an opportunity to come back down in Portland and do it as well. If you want to stay connected, you can find me on LinkedIn. In my day job, I work on tools that some other like larger robotics companies use and self-driving car companies, basically building their data and AI pipelines. So if you want to talk to me about robots of any size, come talk to me at the break. And then also I'll mention we're hiring. So if you want to check out anything on our career page, you can do so. We don't really use MicroPython, but we use a lot of other Python. And then you can find me on GitHub and find the code and resources there as well. But yeah, definitely find me in the break if you have questions around like getting started with microcontrollers or building your own little robot. Otherwise, that is my talk, and I think I'm actually around right on time.